All right, guys, so today we're finishing up the lesson that we started yesterday. Um, so go ahead and get out those notes, and if you need to pause the video, go ahead, but we're just going to be adding to what we were doing yesterday. All right, so let's take a look at this. The table below gives the height of water in a fish tank as a function of time. So in other words, this top row here represents the amount of minutes that have gone by, and this represents the height of the water in the tank in inches at each respective time. So number one is asking us to find the average rate of change. Okay, that's just our little formula here that we're used to, where you find your two time values that you're concerned with. So here we're looking at the average rate of change on the interval from 2 to 7. So here's where t equals 2, and here's where t equals 7. So we're using these two data points to find our average rate of change. Okay, so we're looking for h of 2. No, sorry about that. H of 7 is our t2 minus h of 2. That's our t1. And t2 minus t1 is 7 minus 2. And now, according to our table up here, h of 7 is 18.5. And h of 2 is 10. Continue my work over here. 18.5 take away 10 would be 8.5. 7 take away 2 is 5. And then I guess if we wanted to go a little bit further, we would get 1.7 as a final answer there. Now we want to include our units, okay? So let's back up a little bit. H of t is what's on top, right? H of t is in inches. So the top number comes from the h of t, which is the inches. The bottom numbers are time values, and our time is in minutes. So this is in minutes for 5 minutes. So basically the height of the water went up from 10 inches to 18.5 inches for a total change of 8.5 inches in a time span of 2 to 7, which is 5 minutes. So 8.5 inches in 5 minutes is 1.7 inches per minute. So there's our average rate of change on that interval. Now, let's take a look at number 2. Use the given values to estimate, that's a key word there, estimate the instantaneous rate of change. So I don't want an average rate of change anymore. I want an instantaneous rate of change at t equals 6. Okay, so here's the deal. You guys remember that instantaneous rates of change is basically just your derivative. Okay, well, we don't have a function here, so we can't actually find a derivative. And that's why it says estimate. We can get close to what the instantaneous rate of change is, but we're not going to actually figure out what it is because we don't have a function to find the derivative of. So before I begin the problem, I want to demonstrate something to you. So, if I have a curve and I want to find out what's my average rate of change, what I do is I find the slope of the secant line, right? Well, let's say I wanted to find the instantaneous rate of change at this point. Instantaneous rate of change is the slope of your tangent line. Now, what I want to show you guys is that if we pick 2 points that are really close to the tangent line point, so this is our point of tangency here, but let's say, what if I picked a point here and here, and I found the secant line for those? Do you guys see how the secant line through those 2 points, which are really close to the point of tangency, do you see how the secant line almost looks parallel to, in other words, it has the same slope as almost, the tangent line? So the point I'm trying to demonstrate here is that even though we don't know what the instantaneous rate of change is at t equals 6. If we pick the 2 points that are closest to that, then we're going to have a pretty good estimation if we just find the average rate of change at the 2 points closest to that. So at what point are we looking at? We're looking at t equals 6. So notice there's no t equals 6 in the table, but my question to you would be, what 2 points are closest to t equals 6? That would be 5 and 7. Don't you guys agree those are the closest two numbers on the t column here that is closest to 6? So we're going to use these 2 points. And basically the slope between those 2 points are so close to our point of tangency that the slope of this average rate of change will probably be pretty close to the instantaneous rate of change at that point. So to summarize it once again in a simpler way, when you're trying to estimate the instantaneous rate of change and you have a chart where you don't actually have that point, you're going to pick the 2 points closest to it and just do the average rate of change to estimate it. So the 2 points I'm interested in are 7 and 5 because they are closest to 6. H of 7 is 18.5. H of 5 is 15.5. 18.5 take away 15.5 is 3/2. And so if you want to change it to a decimal, you can. That's 1.5. And that's going to be 1.5 inches per minute. So even though we don't know what the instantaneous rate of change is at 6, we could say it's probably pretty darn close to 1.5 inches per minute because that's the rate of change from here to here. And 6 is somewhere in the middle. So that's that. So at this point, let you guys go ahead and that's actually a really common FRQ question, by the way. So something you want to be aware of. You'll probably see it when you start your FRQs for this weekend, actually. But anyway, here's a student practice for you guys. So go ahead and try that. I'll go ahead and display the answers. But so go ahead and pause the video here, and when you unpause it, you will see the answers. Take about a couple minutes. Okay, so for number 1, here's your answer. Or not number 1, letter A. For letter B, your answer is 0.18 feet per minute. But I want to point something out to you. I want you guys to notice how I wrote this, and I would encourage you guys to do the same. What does this represent? That represents the derivative of h at 2. In other words, that represents the instantaneous rate of change when t equals 2. And notice I didn't put equals. That's kind of important. I put a squiggly line because it's almost equal to it. It's an estimation of what it actually is. So the derivative is approximately equal to the average rate of change for these 2 points, because those are the 2 points that are closest to t equals 2. And so you get 0.18 feet per minute. Okay? So let's go ahead and proceed on to the next part. Okay. So before I start this question up, I want to give you guys a little bit of some background here. Yesterday, I introduced you guys to the position function. F of t equals s, right? Where t represents time and s represents the position. Okay. Then I also introduced you guys to average velocity. Average velocity is what you get when you find the difference in the position and you divide that by the difference in time, right? And that tells you your average velocity. Well, what happens if I take this expression here, f of t2 minus f of t1 over t2 minus t1, and I take the limit of that as I let t2 approach t1. In other words, we're looking at an average rate of change here. What happens if when I let these 2 points converge to 1? Well, what you end up getting is the derivative. the instantaneous rate of change. Because remember, an average rate of change is the slope between 2 points, but when you let those 2 points become 1 point, you end up with an instantaneous rate of change, an instantaneous slope, an instantaneous rate of change, or the actual instantaneous velocity. So you end up with an instantaneous derivative, right? So there it is. So the point here is that now, instead of just finding average velocities, we're going to find instantaneous velocities, okay? And that's what we're going to be doing in this question. So, a diver jumps off of a diving board, and the diver's position is given by the function below, where S represents the height. It says S. I probably should put, let me scribble that out, put F of t, where F of t represents the height above water in feet, and t represents the time in seconds. Now part A says evaluate and interpret f of 1. So evaluate means just plug it in. So let's go ahead and do that. 16 times 1 squared plus 16 times 1 plus 32. What would that give me? That'd be 16, negative 16, positive 16. We would end up with 32. Now that's 32 what? I plugged in 1 for t, and I get an answer out. That tells me what f of 1 is. F is in feet, so basically this is the diver's height at 1 second after he or she jumps off the diving board. So that's our interpretation. The diver's height at t equals 1 second is 32 feet. Now I want you guys to notice something. Anytime you're asked to interpret, okay, you want to include all the units that are being asked about. So I tell you what t equals 1 is. It's in seconds. And I also tell you what 32 is. It's feet. So you need to include the units in your interpretation. The interpretation should also include what the story is all about. It's about a diver and the diver's height. So 3 things whenever you are talking about interpretation. I would highly encourage you guys to write this down, because this is something we're going to do all year actually with various word problems. So there's 3 parts to interpretation. You have input units, that's like our time. You want to include the output units, that's our feet in this problem. And then the last thing I'm going to call context. In other words, what's this story about? It's about a diver jumping off the board and we're getting the diver's height. So your interpretation should always include all 3 parts: input units, output units, and context. Okay, so let's go ahead and move on to part B. Like I said, this is pretty important. I would write this down. It's almost worthy to throw in a flashcard also and memorize it. So part B, evaluate and interpret f prime of 1. Well, first of all, let's find out what f prime is. Well, that's an instantaneous rate of change, isn't it? But let's talk about this. If this represents the diver's position or the diver's height, right? What does the derivative represent? Well, we just got through talking about it on this page over here. Where did it go? Let me see if I can bring it back. There it is. When you take the position and you find the instantaneous rate of change of that position, it tells you the instantaneous velocity. So what f prime represents is the velocity of your diver. Okay, so the velocity of the diver is given by the function negative 32t plus 16. Okay, so take away from this so far is that a position function, if you take the derivative of it, you get the velocity function. Okay, and now we're going to go ahead and do part B, which says interpret this and plug in 1. So we're going to plug in 1 into the velocity function. If I do that, I get negative 16. Now, what the heck are the units going to be? Well, we talked about this a little yesterday. the units for velocity are the units of your output. I'm sorry, not your output. Let's go back to this page here again. It's the units of f over the units of t. Even if it's just a derivative, it doesn't look like a fraction anymore, but remember that derivative came from a fraction. And so the units for the derivative are the same thing as they are for the average rate. So it's the units of f over the units of t. So what are the units of this negative 16? Well, the units of f are feet over the units of t, which is seconds. So this diver's velocity is negative 16 feet per second, okay, when t equals 1. So that's our interpretation. So let's go ahead and write down our interpretation here. The interpretation has to have three things, right? It's got to have the context, the input units, and the output units. So check this out. Ready? The diver's velocity. That's your context. That's what we're talking about. That's the story. The diver's velocity. The diver's velocity at t equals 1 second. There's your input unit. The diver's velocity at t equals 1 second is negative 16 feet per second. That's the output unit. So I've got all three parts in there. That's my proper interpretation of part B. The diver's velocity at t equals 1 second is negative 16 feet per second. Now, it's not part of the question here, but I do want you guys to be aware of what does it mean that the diver's velocity is negative? Okay, hopefully you guys know that that means the diver is going which way? Down. Okay? All right. Let's move on. Now, that's one type of question you'll be asked. Is I'm going to ask you to find these things and interpret what they mean, and when you do your interpretations, make sure you include all three parts. The next thing I want you guys to look at is this type of question, just a specific application of this problem. So, now, when you guys, I've seen this question asked in calculus textbooks and maybe sometimes even like on AP test prep books. Part D is what they ask. They ask something like, what is the diver's velocity at the moment he or she reaches the water? Now, the only way you can know that is when they reach the water. So me being the nice teacher I am, I'm telling you now, we need to do that first. So in part C, we need to figure out how long it takes the diver to hit the water. But once you know that, you can figure out what the diver's velocity is when he or she reaches the water. Okay? The way you're going to do that is you're going to find when they hit the water, and then you're going to plug that number for time into the velocity function to figure out what the velocity is at that point. Okay? But let's go ahead and start with part C. So here we go. How long does it take the diver to hit the water? All right. Well, this represents the diver's height, doesn't it? That's his position or her position. But if we're at the water, what's their height? Well, when they hit the water, their height is 0. So what this means is set your equation equal to 0, basically. And now we get to solve this. So the first thing I'm going to do is I'm going to factor out a negative 16 because there's that common factor they have there. And then I'm going to factor this. And then we're going to set each piece equal to 0 and solve. I've done a lot of this stuff many times this year. Hopefully this isn't looking too unfamiliar to you. So t equals 2, and so there's 2 times when the diver hits the water. That doesn't make sense, right? The reason that doesn't make sense is because there's no such thing as negative time, so we're going to drop that out. But what this one means here is that it takes 2 seconds for that diver to hit the water, okay? If you still need to have time to write this, go ahead and pause the video here. But I am going to move on to the last question here. So part D. So now that I know how long it took the diver to hit the water, the next question is, part D, what's the diver's velocity at the moment when he or she reaches the water? Well, we have a velocity function now, don't we? My velocity function, we'll call it v of t. My velocity function is the derivative of my height function, right? So f prime of t, we decided was 32t, what was it again? I forget. 32t plus 16, I believe. Negative 32t plus 16. Okay, now it took 2 seconds for that diver to hit the water, and I want to know what's its velocity. So now I'm going to plug in 2 to my velocity function, and let's see what that is. So this is going to be negative 64. So if I add 16 to that, what the heck would I get? I'm just going to work it out by hand. Sorry, I know you guys are probably faster at that than me, but there it is. All right, so negative 48, and that's feet per second. So the diver was moving at a velocity of negative 48 feet per second at the moment that he or she hit the water. So I'll say all this again to you. I'm going to clear this, so if you need to pause, go ahead. But I'm going to say this again to you. In the calculus question, sometimes they'll just give you this story here. They'll just give you this, and then they'll ask you D, and that's it. But what you need to know is if you want to find the diver's velocity, you have to first take the derivative of this to find the velocity function. Second, you need to find out how long it took to hit the water, and then you can plug it in to actually find out what the speed was. So it's kind of like a 3-step process, but the way they ask it, it looks like you're just doing one thing, but it really takes quite a few steps to get there. All right, so there's that. And then here's one for you guys. Yes, I saved the decimals for you because I love you. All right, so go for it, and I will put the answers up in a moment. So pause the video. In a few moments, you can see the answers. So here's the first 2 answers. S of 0 is 2 meters. The interpretation is the height of the ball when t equals 0 is 2 meters. There's your 3 parts: context, input, output. Number 2, S prime of 1 is 0.2 meters per second. That means the velocity of the ball when t equals 1 second is 0.2 meters per second. And number 3, the first thing you would have done is set your position function with 0. And unfortunately for you guys, it didn't come out factorable. Mean Mr. Bailey, huh? So what do? Quadratic formula. What else? You get 2 answers when you do this, but one of them is negative. The one that we keep is the positive one. You should have gotten 2.2 seconds. At that point, once you know your velocity, once you know the time whenever it hits the ground, to find your velocity when it hits the ground, you plug 2.2 into the derivative of your position function, and you would end up with negative 11.56 meters per second. Okay, so there you guys have it. And I guess we'll call it a day there. So we'll see you guys again on Monday.